Marhaba. Okay, we will continue our study on functions. Okay, so just a quick recap. We defined what is a function from a set A to a set B to be an assignment or a rule which assigns to every element in A, in the domain A, one and only one element B in the codomain B, say. And then we studied special kinds of functions called injective functions. What are these functions? These are the functions which when you choose two different elements, any two different elements in the domain, they will be assigned two different distinct images in the codomain. Okay, so no two distinct elements in the domain will be assigned the same image in the codomain. Today or now we want to study a new property of a function which is called surjectivity. And what is surjectivity? A function is called surjective if every element in the codomain has a preimage in the domain. Okay, let me write it. So definition: a function f from A to B is surjective. Okay, so this is the new term of this session. If and only if for every B in B, so for every element in the codomain, there is A in A, there is an element in the domain such that B is the image of A. So f of A is equal to B. Okay, so in predicate logic, what do we say? For every B in B, there exists A in A such that f of A is equal to B. So all what we are saying that every element in the codomain has a preimage. So let's have a picture here. This is the domain A, this is the codomain B, and say this is the function. Okay, consider this function. So let's call it f from A to B, and notice that this function is a surjective function. Why? Because look at the elements in the codomain. We have three of them. We have B, the codomain contains three elements, and each one of these elements in B, it has a preimage. So this one has this preimage, this one has two preimages, but that's fine, we only want one, and this one has also a preimage. So every element in B has a preimage. This means that this is surjective. Okay, let's have an example of a function which is not surjective. Okay, let me use a different color. Let's use red. Okay, so I want to sketch a function which is not surjective. Okay, for example, this is the domain A, this is the codomain B, and look at, we have three elements here, and we have three elements, or say four elements here. I will map this element to this element, this element to this element, and this element to this element. Let's call this function from A to B G. This one is not surjective. Why? Think about it. Because surjectivity means every element in the codomain must have a preimage. Okay, but in here, in this example, there is this element. Look, okay, the blue element. This element in B has no preimage, and therefore this is a function, but it is not a surjective function. Okay, so next, what we want to say, okay, let's say a comment about this. So this is the question for you: how can you say that a function is surjective in terms of its range and codomain? So think about it. What is the range? The range of a function is the set of the images. But here we say that every element, okay, here we say that what is the range in this example? So this element is in the range because it's an image, this one and this one. So all of the elements in B are in the range. This is the condition of surjectivity, that every element in the codomain must be an image of some element or must have a preimage. So this means that a function, so no, this is an observation, a function is surjective if and only if the range of the function f is equal to the codomain of the function f. If and only if, remember what is the range? It is the image of the domain, and this must be equal to the codomain. Okay, so this is a nice observation, that surjectivity means that the range is exactly equal to the codomain. In general, the range is a subset of the codomain. But when they are equal, this means that every element in the codomain has a preimage, which is surjectivity. Okay, so now let's take an example. So I want to ask you this question. Example, consider again our friend, the function g from z to z, where the image of an integer is its square. Now, the question is for you, okay, is G surjective? Yes or no? Okay, what does it mean to be surjective? Again, first let's look at the behavior of this function. So we've seen this before. Let me do this. So first we have, say, -3, -2, -1, 0, 1, 2, 3, and so on. Here we have another copy of, this is the codomain. Look, the domain and codomain are the same, the set of integers. 5, 6, 7, 8, 9, and here we have the negative integers. Okay, let's see what is the image of 0. It is 0. The image of 1 is 1 squared, which is 1. The image of 2 is 2 squared, which is 4. The image of -1 is 1. The image of -2 is -2 squared, which is 4. The image of 3 is 3 squared, which is 9. Okay, so this is how the function behaves. And the question, is it surjective? Which means, okay, so this is the domain, this is the copy of the domain, this is the copy of the code. And the question for you, is it surjective? Which means, is every element here in the codomain has a preimage? So the answer is obviously no. Why? Because, for example, so I need to give you a particular element in the codomain which does not have a preimage. Okay, for example, -3 is in the codomain Z, but there is no integer, say n, such that in the domain such that g of n is equal to n squared, which is to be equal to -3, right? The square of any integer is a non-negative number, so it's impossible to find a number here. So I'm talking about this -3. It is in the codomain, and it's impossible to find an element here whose square is -3. Okay, so this shows that this function, the square function, is not surjective. Okay. Now let's let's look at another example. Look at another example of a function. Let f be a function from the integers to the integers again, but now f of n is the next one. The image of the integer n is the successor of n plus 1. So again, maybe let me quickly write a copy of the domain. again quickly. Okay, so this is the domain, this is a copy of the domain. Let's write another copy of the codomain, which is also the set of integers. Okay, but now we have a different assignment, a different function. Okay, so what's the image of 0? It is 0 plus 1, which is 1. Okay, the image of 1 is 1 plus 1, which is 2. The image of 2 is 3. The image of 3 is 4. The image of negative 1 is the next one, which is 0. The image of negative 2 is negative 1. The image of negative 3 is negative 3 plus 1, which is negative 2, and so on. So this is the behavior of this function. Now the question for you, is f surjective? So what does it mean, surjective? Again, choose any element. So let's use green. Let's choose this number in the codomain. Does it have a preimage? Yes, it is 1. Okay, let's choose another element, negative 2. Does it have a preimage? Yes, it's negative 3. If you choose this element, does it have a preimage? Yes, it is negative 4. And so on. You can see that whatever integer you choose in the codomain, you will find a preimage of it. Okay, so here f is indeed surjective. Okay, let me convince you. So let n be an element in the codomain Z. So suppose here we have n. What do you expect the preimage of n to be? I think it should be n minus 1. Okay, right? So now let m be n minus 1, and since n is an integer, then m is also an integer. So which is in the domain. Okay, because the domain of Z, then let's check that m is the preimage of n. So check that f of m must be n. Do you see what we are doing here? We chose any n in the codomain, and we need to find a preimage of it, because this is surjectivity. For every element in the codomain, there exists an element in the domain which is the preimage of it. So let's check that. What's f of m? By definition of the function, it's m plus 1. But what is m? M is n minus 1. Okay, and here we have the plus 1, and this is m. So this, indeed, the image of m is n. Okay, so I just want you to see the order of the argument. We chose any integer in the codomain. We found an element in the domain, and we proved that this element, its image is n. Okay, so this shows that this function, the successor function, is a surjective function. Okay, now let's define a new function. A new property of functions. We've seen injectivity and surjectivity. Now a function which is both injective and surjective is called bijective. Okay, so this is a definition. A function is bijective if and only if it is both injective, okay, and surjective. So what are, by the way, bijective functions are also called bijections. So here we say a bijection, okay, to mean a bijective function, and we also say a one-to-one correspondence. Okay, so all of this name means bijection. Okay, and remember, let me use, okay, we said injective, also another name for injective is one-to-one. and another name for surjective is onto. So if you see one-to-one, it means injective. If you see onto, it means surjective. And if you see one-to-one correspondence, it means a bijection, which means both injective and surjective. Okay, so what is the picture here? Okay, let's unfold the definitions again. Bijective means injective and surjective. Injective means any two elements in the domain, different elements have different images, and surjective means every element in the codomain has a preimage. Okay, so let's draw a picture. So do you think this is a bijective function? Is this a bijection? Yes, it is. Because look, it is injective. All the elements here, whenever you choose two elements, they have different images. Any two different elements here have different images here, and every element in the codomain has a preimage. Okay. Also, here is another example. So usually this is the picture of a bijection. Okay. So look. Here's another example of a bijection. So this is a bijection, and this is also a bijection. Okay, again, why this is a bijection? Look, if you choose this element and this element, they have two different images. And similarly, for any two different elements you choose here, you will find two different images here. And the other point that it is surjective means every element here has a preimage. There's no element here left without a preimage. Okay, let's have a particular example. Okay, so suppose we have the set A, which contains the numbers 0, 2, 4, 0, 2, 4, 6, and 8. And we have another set B. The set B has the elements 1, 3, 5, 7, and 9. Okay, and consider the function f, whose domain is A and codomain is B, where f of n is n plus 1. So again, the successor function, but with different domain and range. Okay, is this a bijection? Is it injective and surjective? Okay, let's sketch the diagram. Okay, here is A, here is B. We have 0, 2, 4, 6, and 8, and here we have 1, 3, 5, 7, and 9. So the image of 0 is 0 plus 1, which is 1. The image of 2 is 2 plus 1, which is 3. Okay, we continue and you will find that this is the diagram of this function f, and clearly it is a bijection. Why? It is injective and surjective. Okay. Okay, so now maybe you may ask, now with injectivity and surjectivity, how many possible cases we could have for functions? Okay, we have 4 cases. Either injective or not, and surjective or not. Okay, so let's quickly see the 4 cases. The first case, a function could be injective and not surjective. Okay, and this is the diagram. Okay, so this is a diagram of a function which is injective but not surjective, right? If you choose two different elements here, they have different images, so it's injective. And it's not surjective because one of the elements in the codomain, namely this one, say star, has no preimage. Okay, so this is injective and not surjective. Now the second case is not injective and surjective. Or if you want, not one-to-one and on-to. So what is the picture here? Let's draw, say this element goes to this element goes to this element, and this element goes to this element. Okay, this is not injective. Why? Because two distinct elements have the same image. This violates injectivity. And this is surjective because we only have two elements in the codomain, and both of them have at least one preimage. Right? Okay. Now, case 3, not injective and not surjective. So we need to violate injectivity and surjectivity. With this one, so we will make two elements to have the same image in the codomain. So this is not injective, and we add a point here in the codomain with no preimage, and so we'll make it, here's another one. Okay, we will make it not surjective because this element has no preimage. Okay. Now the last one is injective and surjective, which means it is bijective. So a bijective function is both injective and surjective, and it has this picture. Okay. So we have 4 cases of functions. Okay, maybe, for example, warning about some assignments. Again, we said this before, but let me repeat it, that some assignments are not functions. For example, this one is not a function in the first place, not a function. Why? Because look at this element, it has two images, and we said that when we have a function, every element must send every element in the domain to one and only one. Here we image in the codomain, here we have two. Okay, let's finish this session by giving you an example of a very famous bijective function. So let A be a set, any set you want. We define the identity function. So this is the identity function. What is the identity function? On A is the function denoted by iota sub A. It has domain A and codomain A, where if you choose an element in the domain, its image will be itself for every element in the domain. Okay, so choose any set, then we have a function called the identity function on the set, where for choose an element in A, it sends it to itself. So the image of A is itself. Okay, for example, if we have the set A, B, C, let's look at the identity function on A. Then the codomain is also the same set, A, B, C, and A have the image A, B have the image itself, B, and C have the image C. Okay, so exercise, prove that for any set A, the identity function is a bijection. Okay, so you need to show, one, that iota is injective, and second, you need to prove that iota is surjective. Okay, let me end this session here.